Layout generation for various scenarios in mobile shopping apps. On mobile shopping platforms, product listing pages are used to display and recommend a number of products to consumers. In order to clearly demonstrate the characteristics of products and quickly engage consumers, the layout of the PLPs, as an essential part, is often created based on shopping scenarios. For example, in the product recommendation scenario, the mall layout of the product listing page consists of several small product cards arranged in two columns. And in each product card layout, the product image occupies a large area. But when we search for a certain product, the layout changed accordingly. The mall layout adopts more larger product cards and arranges them in a single column. And in each product card, the textual information representing the product features is more prominent. In this work, we propose a design space to guide the creation of product listing pages and a novel generative model, LayoutVQ-VAE, to automatically generate product card layouts in pages. In our design space, the scenarios for PLPs are classified into three categories: the scenarios for product recommendation, product by category, and product search. For each scenario, we introduce the mentality and behaviors of consumers enter it, analyze what kind of product information needs to be presented and how to present it, and propose some explicit layout patterns. For example, product recommendation is a scenario showing product recommended by the system, usually existing in the homepage of shopping malls. Consumers enter this scenario often have no clear shopping target and just aimlessly browse. So, PLPs in this scenario need to present as various products as possible, and the product information is mainly presented in the form of images. Externalized to the layout pattern, the mall layout in this scenario usually adopts many small product cards and arranges them in 2 or 3 columns. The design of card layout often chooses a moderate aspect ratio and very few attribute elements, but the image area accounts for a large proportion to attract consumers. Our generative model takes designer input as constraints and generates high-quality product card layout. The training of the model is divided into 2 stages. In stage 1, we leverage a VQ-VAE framework to learn the discrete latent representation of layout by reconstructing it. And in stage 2, we use a unidirectional transformer to model the prior distribution over the latent. After training, the model can sample the latent, matching the designer input constraints with the unidirectional transformer, and generates layouts with the coder of our VQ-VAE. To evaluate the performance of our model, we conducted extensive experiments on 3 public datasets and our PD card dataset, and compared our model with 2 state-of-the-art models. Table 1 shows the quantitative comparisons of element labels constrained layout generation. On both PubNet and RICO datasets, our model achieves the best performance in the evaluation of FID and max IOU, thanks to the discrete layout representation. This illustrates that the layout distribution learned by our model is the closest to the ground truth. In terms of aesthetics, our model also achieves the best or comparable alignment score, which benefits from the discrete representation of geometric parameters of elements. Figure 1 provides the qualitative comparisons. It can be seen that our model produced the highest quality layout, especially with great alignment and rational arrangement of different types of elements. The result of Layout Game++ are close to ours, but some layouts have the problem of uneven size distribution and misalignment of the elements. We also qualitatively evaluate the performance of our model by comparing different generated results, which were obtained from the same element labels but different scenario constraints on PD card and magazine dataset. Figure 2 and Figure 3 show the results on them respectively. By comparing the layouts in the same row, it can be found that even with the same element labels, our model can generate distinctly styled layouts based on different scenarios. For instance, in Figure 3, the layouts for science and news magazines are usually structured and aligned, but the ones for others are more casual and varied, especially for fashion. This results according to our common sense that science and news magazines are more serious and requires rigorous layouts, while fashion and food magazines are prepared for entertainment and leisure, which require more innovative and unconventional layouts. Therefore, we can say that our model is capable in the generation with scenario constraints. Now, let's see how our approach can be used by designers to create PLPs for various scenarios in mobile shopping apps. Given a product recommendation scenario, the designer can make the following decisions based on our design space. Firstly, the product presented on the page should be varied to meet the potential preferences of consumers. Secondly, the mall layout should be in the form of 2 columns and use small product cards. Thirdly, each product card should consist of 1 main image, 0 or 1 title, and 1 or 2 attribute elements of the displayed product. After this, the designer can input the determined UI element labels and the given scenario into LayoutVQ-VAE and obtain several product card layouts that satisfy the constraint. Finally, the designer can place the generated product cards in the designed mall layout and complete the creation of the PLP for product recommendation scenario. To verify whether our approach, including the design space and generative model, could improve the efficiency of creating scenario-based PLPs layouts, we invited 3 groups of designers to conduct a PLP design challenge. The designer group are asked to use general graphic design tools. The template group used 30 product card templates, which are commonly used and provided by an online shopping platform. And the intelligent generation group were introduced to use our approach. After the challenge, 16 participants were invited to assess the quality of PLPs created by the 3 groups. The results show that the intelligent generation group took the shortest time and completed much faster than the designer group. The PLPs they created outperformed the template group in terms of accuracy of matching scenario needs, aesthetic quality, and diversity, and even matched the designer group in some cases. That's all for this presentation. Thank you for watching.